You're here now or no? I'm confused.
Are you ready?
Yeah.
Yeah. Okay. So it's a great pleasure to introduce Martin Zwierlein as our speaker for today. Martin is the Thomas A. Frank Professor of Physics at MIT. He did his undergraduate studies at first the University of Bonn and then the EMS in Paris. They have a master's degree in the EMS before moving on to his PhD at MIT, where he worked in the group of both and did really like seminal experiments observing superfluidity in triple Fermi gases. What's actually not in his official bio is that he was also the captain of our intramural soccer team.
The ball driver.
Yeah, the ball driver. After MIT, he went on for a brief, I think a year as a postdoc at the University of Mainz with Emmanuel Bloch, before returning as a professor in the physics department in 2007. And in his time on the faculty at MIT, he's developed a wide-ranging research program in ultra-cold Bose and Fermi gases and also molecules. He's performed precision measurements of thermodynamics of strongly interacting molecules, some transport properties of interest for condensed matter physics, explored rotating quantum gases as a way of accessing quantum Hall physics, and also really seminal work in quantum gas microscopy, fermions and optical lattices, which I think will be the focus of this talk today. So we're excited to hear about that. I'll mention he has a very long list of awards. I won't read all of them. A few of them are he's a Packard Fellow who's received the Presidential Early Career Award for Scientists and Engineers, the Robbie Prize of the American Physical Society, the Humboldt Research Award, and the Vannevar Bush Faculty Fellowship. We're very happy to have you here.
Thanks so much for having me. It's wonderful to see actually many familiar faces from MIT times, right? John, so we were co-captains of the soccer team together.
I think so, yeah.
Yeah, sorry. I mean, sorry. He was so amazing. I don't know why I was co-captain.
He was the ringer.
Well,
I remember.
We had some battles. It was amazing. Good times. So I'll tell you about these things. Almost look like a soccer ball, right? But look at the scale. Like this guy is very, very small, very hard to study. This guy is not so small, but it's far away and we cannot study it really well. And these guys are very close to human scale, and we can study them really well, but they're very hard to understand. So it's of course interesting to see whether we can find a model method that can sort of help us understand these strongly correlated systems. And so the substance we like to use is an ultra-cold Fermi gas, which are accessible, they're widely tunable. We can induce different interactions. We can change the geometry. We can put them in optical lattices or on tubes or whatever we want. And we can change the spin composition. We can even have like not just 2 spins, but like 5 spins or something like that. Very, very interesting things that Ben, for example, is also studying with his this Procyon. So this is the idea behind it is basically spelled out by Feynman to simulate the quantum system using a quantum system. Like you shouldn't use a classical computer. So there's a bit kind of colloquial style. So if you already know what an ultra-cold quantum gas is, fine. But I wanted to get everyone on the same page because I guess you might be from all kinds of different realms of physics. So on the temperature scale, we are not here in the supernova explosion, definitely not. also the temperature in right now here is very comfortable, but we live down here at the nanokelvins. And interesting thing to realize is that if I was in a supernova explosion, I would be very quick to make it here. I should have said, Boston, Stanford would be 10 seconds. I would not make it in one piece though. This is the typical speed of a particle in the air right now, bumping up your cheekbones, hundreds of meters per second, still pretty fast, and our atoms are very slow, as you probably already know. But now, if that was the only thing, it would be a bit boring. So luckily, it's not just slow, but also exciting, because as you go slow, then your de Broglie wavelength starts to matter. Right now in this room, a sodium atom would have a de Broglie wavelength that's on the size smaller than the nucleus of the sodium atom, so we don't care. But at low temperatures, these things become measurable, as I will say. Another way to think about this is Heisenberg's way of saying there's an uncertainty. If you start to cool down, you know the velocity of your particles better and better, and that means you no longer know where they are. They're spread out over an uncertainty block. So if I now have a cartoon of my gas in the air, I could maybe draw them like billiard balls, but really I should draw them as little quantum wave packets, which then at low temperatures start to spread out more. And now I get into this identity crisis. Yeah, I don't know. Am I here? Am I there? Am I together with other atom or not? So as you know, we have to now learn quantum statistical mechanics to learn about fermions and bosons. Fermions hate each other, don't like to be in one quantum state, and really try to avoid each other. They're very antisocial. This guy's spying on everyone. This guy's listening to music. This guy's polyblocking himself. Terrible people. And then the bosons are very happy people. They help each other into the ground state that's called bosonic simulation, where they form a Bose-Einstein condensate. So there is a phase transition. Cool. So then the cartoon would continue for the bosons, that everyone becomes one big happy wave. So you have, for example, in typical experiments, 10 million atoms all sharing one and the same wave function. And hey, we have now 30 years of BEC. So it's actually a wonderful thing to celebrate, not only 100 years of quantum mechanics, but also 30 years of BEC. So that's cool. Fermions live this sad life where each one has to be in their own little box. This is a cartoon I made in, I think, roughly 2012 or so. And I thought, that's just a cartoon. It's hilarious. But these days, people can actually put fermions in optical lattices. And if they put the like spins in an optical lattice, only spin ups, say, then actually they avoid each other, just like on this picture. And I'll show that in a few slides. Let me get back, though, to this very interesting moment when we start to have this identity crisis. Can we somehow see this situation when these wave packets start to overlap and quantum statistics starts to matter? Can it be more than just a cartoon? And so we just built a setup where you can actually do this. We have our quantum gas in an optical trap, this red thingy, and they might do their merry thing. Who knows? Maybe they're classical, maybe they're quantum. But in one moment, we say freeze, switch on an optical lattice to make them stop in their tracks, and now we image their positions. And so that gives us images like these, where you see actually a Bose-Einstein condensate, but now with countable number of atoms. You can see each single boson in this image. Kind of cute. It's the world's smallest condensate, probably, at the moment. If you do it with fermions, you immediately see they hate each other, right? They really don't like to be near each other because they're like fermions. So that's actually a direct visualization of the quantum statistics happening. If you do it with a thermal Bose gas, you see how they clump, how they like to bunch up and be near each other. And therefore, if you now plot the G2 function, the probability for two bosons to be near each other, you do see you see this bosonic enhancement up to a factor of 2, so it's twice more probable to find two bosons on top of each other than just by mere chance. No, so that's the thing. And what is the width of this feature? It's just the de Broglie wavelength. It's precisely this range over which I have this identity crisis. If you do it for fermions, you observe instead the Fermi hole, the fact that the fermions don't want to be near each other. So that's directly coming out of images like these. The de Broglie wavelength here at low temperatures saturates to the interparticle spacing. So that's the de Broglie wavelength at low temperatures for fermions. They have to keep a distance from each other given by one interparticle space. So that's cool. So these kind of images directly now give you a microscopic view of correlated quantum matter, and we should later apply it to interacting systems and see what happens. So that gets me to the hope of studying interacting systems. These are all complicated interacting things. And it gets really complicated once you ask for dynamics. Would it not be nice to have a first principle understanding of how nuclear fission comes about? We have these superconductor objects which above the superconducting dome are very strange, which you can read off by seeing that we gave strange names to the phases. Strange metal means we don't understand the metal. Pseudo gap means we don't understand why there's a gap. So these are interesting states where apparently the transport is exotic, and maybe you can hope to understand it. On this right side of things, you can imagine what happens in one of these neutron star mergers that they now see with LIGO. Probably there's all kinds of complicated friction going on between these fermionic systems as they rub against each other. The typical way we study these Fermi systems is either we are given an atom that can have very strong interactions, wonderful, then that can already be a strongly interacting Fermi system on its own. I will tell you a little bit about some work in this regime of continuum physics, so atoms in the bulk interacting strongly. But you can also switch on an optical lattice and quench the role of kinetic energy and thereby promote interactions. And then you see interesting phenomena with direct relevance to condensed matter physics. So I'll talk about both as we go. Maybe first on the bulk situation, which is very close to what we just saw, but now I have two spin species. You can study a crossover of a Bose-Einstein condensate of tightly bound fermion pairs to a Bardeen-Cooper-Schrieffer state of long-range Cooper pairs by just tuning the interactions between spin up and spin down. So for very strong interactions, they form molecules. It's just a BEC, just a Bose-Einstein condensate. And for very weak interactions, there is always a bound state for two particles in the presence of the Fermi sea. That was Cooper's inside, which then led to the BCS ground state. And by just tuning a knob in the lab, which is the magnetic field, turns out we can actually change the interaction strength and go from one regime to the other. So we have done this for a long while, and it's embarrassing almost to say, wow, this is now 20 years ago, because that dates me. Can no longer claim I wasn't born then. These images show that we have a superfluid of fermions, because as you rotate these gases, they do not form just one big whirlpool like in the bathtub, but these vortices need to stay away from each other. That's their way to minimize the energy in the system, and they form these beautiful Abrikosa lattices. And it's cool to think about. I mean, this is happening at nanokelvin temperatures, yes, but if you scaled this gas to the density of electrons in a solid, you would get a TC, critical temperature, far above room temperature, which is cool. So that's sort of making us hopeful that in principle, if someone, that's very likely not us, finds a way to make electrons very strongly interacting, then, why not? You could have a room temperature superconductor. In fact, on the chart of superconductors, our gases occupy a nice spot. This plot shows the critical temperature of superconductors versus the Fermi temperature. This is called the Umura plot. Professor Mura is in Columbia. And you see all kinds of superconductors. Maybe the conventional ones are over here, very low TC compared to their Fermi energy. So that's the story of electron-phonon coupling being very weak, and you get an exponential suppression of TC compared to the Fermi temperature, or even compared to the Debye frequency. But then there are all these super interesting ones that are strongly interacting, and their TC comes very close already to the BEC critical temperature that you would get from a bosonic fermion pair. And our gases are closest to this BEC critical temperature line. And of course, to put them on the same plot, you have to multiply all numbers by 10 to the 8, because everything happens, of course, at nanokelvin. So this is actually from a paper by my friend and colleague Pablo Herrero, where they presented twisted bilayer graphene being effectively high temperature superconductor. So you might now wonder, okay, this is a very interesting gas. What about the equation of state? It cannot be this simple, I guess. We love P equals NKT, but what is it for this strongly interacting soup? Maybe more related to neutron stars. So it turns out there's a direct relation between this equation of state of our dilute atoms in our experiment and the neutron method, very like dilute neutron method. And the comparison is, of course, okay, it's all spin 1/2, fine. In the particle spacing, it's very, very different. We have 1,000,000 times thinner than air kind of gases. And in the neutron star, you have like 10 to the 38 atoms per cubic centimeter. Okay, so 25 orders of magnitude difference, but the relative scales are the same. For example, the scattering length, well, for us, it's freely tunable, but importantly for them, it's a much, much larger and negative than the interparticle spacing, minus 19 femtometers compared to typical femtometer interparticle spacing inside a neutron star. So neutron stars are also in this unitary regime, as we call it, where the scattering is as strong as quantum mechanics allows. And so we measured the equation of state at some point as a function of temperature and found what the ground state energy was. It was 37% of the ground state energy of a non-interacting Fermi gas. And it turns out then there are recent papers where they actually try to get the energy per neutron in dilute neutron method. And I was so happy that they use the unitary gas as one of the lines in this thing, which provides a sort of a bound. They think it's a lower bound for the energy density of neutron method. And it's doing quite a good job. All the other stuff is like different theories. It seems to be such a commonplace by now that they don't even cite us. Great. Okay. So now let's apply this microscopic view of these fermion pairs to the this microscopic view that we introduced before to the case of interacting fermions. And that works surprisingly well. I mean, it was kind of amazing once we had the single atom imaging working. It was then pretty much a piece of cake to also apply it to this interacting gas. And you take these images and you see, whoa, they're very often two guys next to each other. Here they're actually so close that you don't even distinguish them really. But then as you tune the direction, the pairs become larger in size. Now I draw these ellipses, this is a little bit of a gut feeling thing. There's no scientific way of drawing these ellipses. I'm just pointing out.
Those aren't detected ellipses.
So I should say the ellipses are drawn by hand, by a human, not by AI even. And using a completely arbitrary criterion of beauty and
Kind of non-linear.
it was a very non-linear human eye that was doing this. Just to sort of point out, how these fermion pairs change. A little bit more scientific comes in a second, but I should say a few weeks ago. So by the way, so this was all red. You might be like, hey, I thought like fermions don't like the true, but this was an image of the total density. At that time, we did not distinguish spin, and as of a few weeks ago, we actually do manage to detect spin, which is a little bit of some acrobatics. You have the physics happening in one layer, then you freeze. Then you split into two layers and image this layer and that layer separately. It's acrobatics, but it works out. And if you do that, you actually see by eye. Okay, let me just draw the ellipses again. Okay, there they are. You see by eye that these guys like to be near each other. I mean, we're not surprised. That was the story all the time. But like, I found it cool to see it directly in these images. So. Now, instead of ellipses, let's be a bit more scientific and draw, again, the G2 correlation function. For the light fermions, the blue stuff, you already know this. Those are the Fermi holes. They still don't like each other, absolutely. But the total density, which is the red stuff, there you do see this enhancement at short range where they actually like to be near each other. And the blue and the red curves are taking the functional form from BCS theory, but allowing the parameters to be flexible. So we're not fixing things like the pairing gap or chemical potential. We let it let it flexible, just to have a nice fit function to measure this thing. And it works quite well. Yes.
Your red curve here is looking at opposite spins or just total density?
This total density. And if I was prepared, I would have brought the difference density, because we can take the difference of these two, and that would give me the up-down correlation function, which would be even more enhanced. We actually did this for the resubmitted version of the paper, because it is indeed quite nice to point out the G up-down. Yeah, but this was again from the images where we did not spin resolve, so this was directly coming out of the images. Whereas now from this data, we directly have G up down. But again, I'm not prepared to show that to you, but that's the thing. So we're gonna do this for like a whole range of interaction strengths, and it's going to be fun. Yeah, so that is what we can now get from these local resolution type of images. I think this will have a lot of fun looking at various other states with this method. So great, so we see the microscopic correlations here now. Now I wanted to also tell you a little bit about transport properties, what is cute about these systems, and I'll talk about both density and heat. And if you have some new soup in your lab, as a physicist, you always feel the urge of tapping it, shaking it, doing something with it, right? So here we have a box of these fermions it's a box of light, green light confining these atoms. So we have homogeneous density, and then we just tap one side of the box to see whether we create some ripples. It works. To enhance it, I'd subtract the unshaken image, and you really see the sound waves propagating happily. And you see, most importantly, that the sound waves are damped. As I shake one wall, they're damped. And that damping is very interesting because that teaches you about the viscosity of the fluid and the thermal conductivity. Both of these contribute to damping of the sound wave. To just show a few more things you can do, it's fun. You can basically sing to this thing. 400 hertz, I can totally sing this. I will not sing it right now, but it's basically what you would be able to sing. You should use a Bose loudspeaker, by the way. And then you can create all these different sound wavelengths. It would be more expensive, much. Yes. He was an MIT guy, so maybe I get a discount. Yeah. So that's yeah. And let me point out, we have a gas here, but we have a linear dispersion. So I mean, maybe by now you're not surprised anymore, but it's cool, right? Out of a gas, which is supposed to have a quadratic dispersion, you actually get something that carries sound modes already in the normal phase. By the way, it doesn't have to be superfluid for that. Even more fun is when I do this in my bathroom. It is a lot of fun for me, not for the family, but I sing and try to find the resonant modes of my bathroom. And this works. You can just scan the frequency and sing to this thing, and you get all these standing waves in your box as advertised. I mean, this is basically you could use this. You could teach this to undergraduates, a way to measure sound resonances in a box. And from this, well, you can take all these standing waves, integrate over the boring direction, and then stitch together all the frequencies to get the sonogram if you want. And you see the low frequency modes are very narrow, then the higher frequency modes become broader and broader, and so you see more and more damping at higher and higher frequency. You feel the urge once you see this to take the Fourier transform to actually plot it versus k, the spatial momentum, and you do see a linear dispersion again. And you see also, if you squint your eyes, a little bit of a second harmonic, yeah, which at some point we should analyze a bit more carefully, but it's cute. So then you get all these sound resonances as a function of for the various modes that can live inside the box, and you see how they get broad. At this point, you have to hit the books. You're like, I have a new soup, I don't understand hydrodynamics. So you have to hit the books and learn about how to derive sound damping from starting with the continuity equation, starting from Navier-Stokes equation, which has the transport of momentum in it, and as a damping mechanism, viscosity here. For our gas, there's no bulk viscosity, only shear viscosity, little detail. And heat transport, which comes from energy conservation. That can also cause damping because heat transport is damped through thermal conductivity. You shake these three equations and get a dispersion relation out for the modes that can live there, and you realize there's sound waves that live in there, which are damped by a combination of viscosity and thermal conductivity. Don't worry about the rest, it's like temperature, pressure, and density, so on. The dispersion relation is almost linear. Can you even see this in the back? Oh, there's another screen here. so omega is almost ck, but there is a little bit of damping, which always goes like k squared. There's a diffusivity in front times k squared. Why k squared? Because it's always the curvature of the velocity field that causes damping, viscous damping, and not just the gradient of the velocity field. Gradient is fine. So we get a damping rate that should grow with k squared if it's a hydrodynamic fluid. And that's what we see. So we plot the damping rate versus frequency, and it's more or less, I mean, I can fit the parabola to lots of things, but it does work quite well. And I get a diffusion coefficient, which without me putting any quantum thing in here, I just take the frequency and damping rate. I get 2.1 measured in Planck's constant divided by the particle mass, which is actually nearing the quantum limit of sound diffusion. So at that point, it becomes interesting to ask, what do we know about other quantum fluids? For example, helium-4. I learned it's a superfluid. Shouldn't it have zero viscosity below Tc? No, careful. That sentence is only true when you say in narrow capillaries. So if superfluid helium propagates through narrow capillaries, yes, the normal fluid is clamped by the walls and the superfluid goes without friction. Awesome. But if you have a bulk container of superfluid helium, there is still sound damping because of the normal fluid that's around. And so the viscosity doesn't go to zero. It reaches a minimum, which they measure to be 10⁻⁸ meters squared per second. Whoa. And then it goes up again. I can tell you why. It's because only phonons survive at very low temperatures, but let's leave this for later. But why didn't they use h⁻m as the y-axis scale? It's so nice. It's actually on the order of h⁻m, superfluid helium-4. What about helium-3? We have a Fermi gas, so we should compare to helium-3, not helium-4. Very different story. At low temperatures, the viscosity of helium-3 becomes extremely sticky. It starts out when it becomes liquid at a level which is h⁻n, already the quantum limit, basically, or on the scale of the quantum limit. But then it keeps growing like 1/t². That's because of Pauli blocking of collisions. You start forming a better and better Fermi C, which has a width given by the temperature. And so only those guys near the Fermi surface, they contribute still to scattering, and that gives you a viscosity that goes like 1/t². So it becomes extremely sticky. And then helium-3 also becomes a superfluid, yes, but that doesn't help so much. It helps roughly a factor of 10 in viscosity. But what is the level that the viscosity levels out to be? It's still 1,000 times h⁻m in superfluid helium-3. So it's as sticky as honey. And I can tell you why 1,000 if you want later on.
And similarly delicious.
It is, depending on the observer, it is delicious. To some. I find it delicious. So this is now what we measured, quantum limited sound diffusion at low temperatures. First of all, it goes down, not up, okay? So we do not seem to see any effect of Pauli block before we become superfluid. The reason you can almost see by eye, the temperatures here are measured in units of the Fermi temperature, and they're not very small compared to the Fermi temperature. Superfluidity kicks in already at slightly below 20%, and that's not a very sharp Fermi surface to start with. So if there is Pauli blocking, it hasn't kicked in any significant way yet for us to first see an upturn. We should repeat the experiment in the far BCS regime. Maybe there we should actually see this Fermi liquid kind of behavior. And then it settles down to something on the order of h⁻m. It is a bit an underwhelming curve in the sense that nothing special happens at Tc, right? So it's not very super here as I go from normal to superfluid, which brings us to the question, what is super of a superfluid? In fact, that was thought about by Tija and later, Landau, the priority here. The realization that I could describe superfluid helium ideally as two fluids. One which is super duper, doesn't give you any damping, and one which is carrying viscosity and all that normal stuff, right? But if you have two fluids, you should get two sound modes, right? And indeed, that's the case. And the interpretation is one sound mode is just the standard sound where superfluid and normal fluid go together. And the other fluid is, the other sound mode is in an entropy wave, almost purely entropy wave, where normal and superfluid oscillate out of phase. And the density pretty much doesn't change. So that gives rise to two sound modes, first sound, second sound only kicks in at TC. It's kind of low and rises at very low temperature. So we felt like that would be nice to see. It would be cool if you could see that second sound directly, but we wanted to see it in the heat. But how do you measure heat was the question. There comes, atomic physics is rich in spectroscopy tools, right? So you think about, can I use spectroscopy somehow? I remember Planck's radiation law. That told me something about temperature as I figure out what the peak of Planck's curve is, right? I can see there's a glowing metal bar. I can get the temperature. Or I look at the sun, I can get the temperature. So maybe we can look at some spectra. The spectra we use here are radio frequency spectra. I can flip a spin of my interacting soup into another spin state that is let's say ideally non-interacting. It's not non-interacting, but it's not occupied before. And without any interactions, that's how atomic clocks work. So I know this with atomic clock precision. But with interactions, of course, it takes an additional amount of energy to free up this little spin from this interacting soup. So there's a clock shift, as we call it. At low temperatures, it is shifted by an amount on the order of the Fermi energy. And then as you increase the temperature, this peak shifts to the left. That's all I need. I don't need to understand those curves. I just need the fact that I have a spectrum that depends on temperature. That's all I need, because now I can use this as a thermometer. So I just sit at one particular frequency, more or less randomly chosen, where I get a nice discrimination between a cold, hot, and hotter gas in the response in the radio frequency response. So take the single frequency, I actually know what the temperature in my gas is. And as a little cartoon, it's not needed, but you can also have a little cartoon idea of what we're doing. If we tune our radio frequency to the atomic transition that we know from atomic clocks, we are only going to transfer free atoms and not bound atoms. So down here in this cartoon that you cannot see in the background, like there's this copy, but my laser pointer doesn't really, it's very hard to see the laser pointer. So I have a mixture of a normal soup of broken pairs and a superfluid soup of pairs. In that situation where I tune myself to the atomic resonance, I only transfer those broken pairs and not the pairs. So then I directly have a picture of heat. I directly see the gas of excitation. So that actually works. So this is a density profile of our trapped gas, very boring looking. But here is the spectroscopy acting on it, the temperature probe. And I see, actually, in this experiment, we heated up one side and cooled down the other side in ways that I can tell you in a second. And the thermometry is actually quite sensitive. You can make out less than a nanokelvin difference between the various regions. So the amplitude here in temperature is just plus minus 4 nanokelvin. So with this new technique, you can actually watch heat slosh back and forth in your superfluid. So this is a quite pixelated movie, but still it works, this heat channel, this radio frequency channel that tells us where the heat is. Let's start here again. We start hot on the lower side. After some while, we find the hot stuff on the upper side of the box. And it comes back down to the lower side of the box, more or less. And here you see the traces of the movie. And it's a wonderful wave. And here is a cartoon picture of what happens. The superfluid and the normal fluid, they trade places, but the total density basically doesn't change. Yeah.
How can I see if the density is changing?
You cannot. From this, you cannot. You can only see the RF response, but we can simultaneously look at the density response and actually disentangle temperature and heat response. And so we did verify that the case that the density is almost not changing a little bit. It is actually changing because the gas is a little bit compressible. So that immediately means that there is some coupling between density and temperature. And therefore, indeed, the density does change a little bit.
Like in phase.
Yes, actually. So you can also look at the density, and you will see a small amplitude oscillation at the same frequency in the density as well, because density and this heat channel, they are slightly coupled. Because of the non-zero, the fancy word is expansivity, the coupling of density to temperature. But it's actually nice with the density and the RF probe, we can actually disentangle those things and provide the density response function and the density heat response function for the experts, and plotted versus frequency and fitted to the predictions of the true fluid model, which then as the output gives us the diffusion coefficients for first and second sound.
But can you, I guess, like explicitly include that like compressibility into that model that you're doing, put that out separately?
Yes, so the compressibility we basically know from static experiments where we just look at a particular, usually that's easiest to done in a trap where you naturally change your potential and you look at the density change with respect to that potential, and that gives you directly the compressibility, dN dV. That's how we actually measured the equation of state back in the day. So we have the compressibility in our hands as a thing that's already put in, and so that actually helps to tease out these new parameters that only have to do with transport, like the diffusivity. Nice. Super. Awesome question. Anything else? Any other questions? I didn't stop for questions before. Cool. Feel free. I'm like in this excited mode. I might forget to pause for questions. So it's actually a nice way to see the superfluid transition. In a normal fluid, you make one side hot, it just boringly exponentially decays that heat. But in a superfluid, it oscillates back and forth. So that's a very nice way to distinguish normal from superfluid. And these colorful graphs show nothing else than stitching together all these data into a colorful plot. That also allows us to now measure the second sound velocity as a function of temperature, which properly should go to zero at the critical temperature. And from that, turns out that some more hydro that we have to learn, you can actually back out the superfluid density of the gas, like how much of the stuff is actually superfluid. And this works quite well, both with some theory expectations, but also with the beautiful experiment by Rudy Grimm in quasi 1D Fermi gas, where they already measured second sound, and they needed as an input the equation of state to back out their superfluid density. But here it shows they did a good job. it actually worked out. Great, so that was the continuum world. I will now move to the letters, but maybe it's another good point to pause and see whether everyone is happy. Let's go to the letters. Okay, so we have these two ways. We can have strong interactions either by just having them, awesome. So maybe we have some Feshbach, maybe we have some dipolar interactions like in Ben's lab. Complicated to say. Or
How much caffeine did you give him?
well, so first I came with the coffee, then I saw that there was this tea. So I chugged that tea, and then I had another cup of coffee. Yeah, that's actually very good. It's very good. It's very good. That's very good. I'm actually getting to the temperature right now. It's actually going well. So here we have this other way that I promised to promote the role of interactions. That's quenching the kinetic energy, putting these guys in optical lattice. There are more sophisticated ways to doing the same thing. If you take graphene and you twist a second layer on top of it, that's also a very fancy way to actually create flat bands and momentum. Or you start rotating your gas, or if you have charged particles, you apply a strong magnetic field. That gives you Landau levels, also flat dispersion, also interesting physics, because interactions now dominate. So that's all exciting. I guess that's hey, yeah, thanks. Yeah, you know me. He knows me really well. He knows me too well, actually. Shouldn't have said that. Okay. So we go into this regime here. Once you're on the lattice, if you go to the lattice, okay, so everything discretizes. You see like lattice sides, and instead of freely moving, I hop from one side to the next. And if I'm together with another unlike spin, I have interactions U. In cold gases, we can tune U, which is nice. So we can make it attractive or repulsive. Usually people are interested in the repulsive Hubbard model more than the attractive one because, well, electrons repel. And the hope is that somehow in this Hubbard model, there's D-wave superconducting dome, but we don't know that yet. In fact, some indications are that in the plain vanilla Hubbard model, we might not have the ingredients necessary for D-wave superconductivity, but it's not known yet. Let's see. So this is a phase diagram of the cuprates, which immediately tells you it cannot be plain vanilla Hubbard because whether I dope electrons or I dope holes, I get a different, slightly different phase diagram. So that's not particle hole symmetric, but the Hubbard model is. So we know this cannot be the full story. But yeah, let's see where one goes. With cold atoms, of course, we love these single atom resolved images ever since Marcus Schreiner produced those for bosons. We got very envious and wanted to have that for the fermions. Marcus with Racine and Emmanuel Bloch with Stefan Kuhr in Munich produced these images of bosons and optical lattices. And I think that was a revolution in the whole field to now be able to actually see quantum physics atom by atom. And so now for the fermions, there's a whole bunch of color codes that people came up with. You can still add yours. We didn't run out of colors yet. And this slide is no longer complete, as you can imagine. I stopped in 2021. I'll tell you a little bit about the more recent work from our group. I will not tell you about the very fun fact that fermion pairs can also be a qubit. Ask me about this later. I'll not tell you about that. I will tell you much more about fermion pairing, as this is sort of in line with the first part of the talk, and a very little bit on the repulsive Hubbard model. Here comes the repulsive Hubbard model, first things first, which is happening in a trap. So you have an overall trap switched on. That means the high density regimes are, of course, in the center. That means you get 2 atoms per side in the center. You cannot have 3 atoms per side because you have only 2 spin states, and we are thinking about the single band Hubbard model. We gap out the other bands of the optical lattice. And why is it so bright? Well, because in this experiment, we are able to distinguish 2 from 1 atom, again, with this bilayer trick. And so in the center, you have a band insulator. Outside, you have a Mott insulator of 1 atom per side. And then as you weaken the repulsion, you start to see this mess, this, you could say, garbage. It looks hot. It's not hot. It's a strongly correlated metal where the particles run around in weird ways. In the middle, you see sort of the first glimpse of what happens as you heat up, well, not heat up, as you have a little bit of weaker weaker repulsion, coffee kicking in your Hubbard model. You see these weird blips. You see these blips, the bright and the dark bright and the dark bright and dark. Those are double hole pairs that are naturally an ingredient of the repulsive Hubbard model, because the atoms would like to form singlets up here, down here, up here, down here. But of course, there is a little bit of probability amplitude to hop on top of each other, creating a double hole pair. So the cartoon is down here. It's all a little bit in the lower left corner. I don't know whether that screen helps. So you have these double hole excitations of them that are coherently mixed in, even in the ground state. And you can see those directly under these microscopes. Of course, you can still do the old way of just plotting density versus potential and getting the compressibility out and getting the pressure and all that. So you can have the equation of state. And all those together give you a very nice picture of what's going on. In fact, I should also say it's nice that fluctuation dissipation theory connects those 2 worlds to give us a direct measure of temperature. So we do not need to fit to the favorite theory. We can actually directly get temperature by looking at the density fluctuations and relating that to the compressibility, which gives us temperature. But I want to focus on the attractive Hubbard model, because that's more in line with what we learned before. No surprise, once these guys attract, that there should also be fermion pairing going on, and there should actually be a BEC-BCS crossover again. At large attractive U, they should form small bosons. At weak attractive U, they should form a Bardeen-Cooper-Schrieffer state. And in between, it's going to be some strongly correlated in-between SU, where there should already be pairs above TC. It's very good for us because we have a hard time cooling into the superfluid regime, I must admit. To be also honest, we don't have a super good probe at the moment for knowing when we have achieved the superfluid in this system, unless we maybe figure out second sound in that experiment as well. So we think we are roughly here at this temperature regime. We figure this from the fluctuation dissipation theorem, which we apply assuming there's no condensate. Ask me later about this obscure sentence, if you want. There is one more ingredient other than what we know from the bulk, and that's another way that the system can be very, very happy in the lattice, and that's a charge density wave. You can have the pairs, yes, but they can also organize not in the superfluid state, but in a crystal, the charge density wave. Double on hole, double on hole. And at half filling, it is as good a state as the superfluid state. And in fact, the order parameter therefore has 3 components: x, y corresponding to the superfluid order, and z corresponding to charge density wave order. It's pretty cool. Actually, the totally mapped version to the repulsive Hubbard model where you have x, y, z antiferromagnetic states. That was for the experts. So it's cool. So we should probably be seeing some glimpse of charge density wave. Let's look at the images with full spin and charge readout. So we look at the spin ups, we look at the spin downs, we combine those images to give you the total density here on the left, and on the right it's the digitized version where white means I have found the doublon. And there's also, you cannot see it in the back, but there's also red and blue dots for the singulon up and the singulon down fermions in this soup. But I already see some structure where it looks like a charge density wave fluctuation. Let's use that probe to turn on attraction on this Hubbard model. This is non-interactive, and there you, of course, by chance, you might have some doublons. But as you increase the attraction, more and more of these pairs form, you get more and more of these doublons, and then eventually they start to organize into this sort of checkerboard pattern. Let's see. So this is actually very similar to in spirit, apart from the charge density wave, from what's happening in this bulk BCS crossover. And let's look at the regime of rather tightly bound pairs. There, most of the images are white, right, full of doublons. But every once in a while, you see also singulons, singulon blues, singulon reds. And don't you think that they're very often next to each other? They're very often next to each other. And that makes complete sense. I have a pair wave function, which is not just I'm a doublet, but I can also spread my wings a little bit and sometimes have a delocalized component. And that's mixed in by an amount given by the tunneling, normalized by the interaction strength. So the stronger the tunneling, the more I like to do that. And you also see these patches where there's a charge density wave. If you weaken the attraction, now we get way less of these doublons, and it's more like a terrible soup of blues and reds. To know whether you have pairing here, you actually have to analyze 50 shots of the experiment and do statistics and see whether for every spin up, there's always a spin down around that paired up with me. And that is the case, which is why I allow myself to draw these human intelligence ellipses again. This is just a cartoon. I don't know who is married to whom, but this is roughly the picture of what's going on. And we know this from analyzing the spin correlations. So that's maybe the thing that I can still, I have no idea what this clock is doing. Oh, okay.
Can I ask a quick question on the last slide?
Of course.
I'm a little bit ignorant about this. So does the CDW extend down into superfluid so you would actually have a super solid? Or does it die?
That's a super good question. I had the same question to my theorist friends. So from the simulations, it seems it remains as a fluctuation on top of the superfluid, even down to 0 temperature.
Okay.
So it will not be in 2D, it will not be super long range. It's but you know, as much as you could call algebraic order in a finite system a pretty healthy thing, it has a flavor of a supersonic. So that's actually exciting to see whether that's actually true or whether the theorists have some problem.
It'd be a situation where they would break the symmetry simultaneously, whereas all the other systems, more or less, it's kind of one's imposed or comes in differently than the other.
Yes. Yeah, so I find this interplay with the charge density wave super interesting. We haven't really started to look so much into it yet, but like I think it's very interesting to see what happens at lower temperatures. Yeah, super good. Yeah. Let's look at the spin correlations to see whether down is married to up. So what we do is we look at the magnetization fluctuation. So if you see a spin up, is there another spin up nearby? Yes or no? And without interaction, there is already a correlation. That's just the Fermi hole. They don't like to be on top of each other. I called it the Pauli hole here before I read Wigner's paper where he says it's the Fermi hole. And since then I switched to Fermi hole. Very, very sad. Some people call it Pauli hole. If you switch on interaction, now you actually have an additional correlation from the fact that these guys want to be, the unlike spins actually want to be near each other, which increases the range of these spin correlations. And for very strong interaction, the correlation length decreases again, because now I have such a high energy cost to sort of fluctuating to the neighboring side where I'm not profiting from the attraction, that it's very strongly suppressed. And therefore I get only a small next neighbor correlation here in the high U limit. Cool, so that actually is the picture. And we can sum up these images to get the total spin fluctuations. And for the super duper experts, this is equal to the spin susceptibility times the temperature. So for any finite temperature, which we unfortunately have, seeing zero spin susceptibility is also directly telling you that you have a paired gas. So we see that spin susceptibility go to zero at some interaction strength. It's not a critical interaction strength, it's just the interaction strength where at our temperature, we start to exponentially suppress unpaired atoms. So that's the idea. We can look at this intermediate interaction strength and measure the distance of these correlations. It's a few sites, not super surprisingly, but what is cool is that it is, of course, a pair that is extending beyond the interparticle spacing. So these pairs are definitely many-body things. It's not a two-body pair that we are seeing here in a dilute gas. It's a very dense gas where we have pairing that goes beyond one lattice side. Okay, cool. That summarizes what we can study in these Hubbard systems. We can study the repulsive side, the attractive side. There's a beautiful mapping that I hid from you between the repulsive and the attractive side. So these double-on-hole fluctuations on the repulsive side are nothing else than the up-down fluctuations of my pair on the attractive side. There's a one-to-one mapping by mapping the spin-up particles to spin-ups and the spin-down particles to holes. Kind of cute, two sides of the same metal. That works for any lattice that is so-called bipartite, like can be split into two equivalent sublattices. So our square lattice does that. What are we doing right now? We're trying to understand the spin-doped attractive Hubbard gas. And this phase diagram is more to say like, oh God, it's going to be complicated. Indeed, once you sprinkle in excess fermions on top of your superfluid, you might think that at low temperatures, you can again get another type of supersolid, which is where these excess fermions form a lattice, and your superfluid forms an oscillatory wave function instead of a homogeneous wave function. That's the full differential Chilikov state. And I told you about the mapping. In fact, this state maps on the repulsive side of the Hubbard onto the striped phase that is found in Monte Carlo calculations for the repulsive Hubbard. So it should be there, and we are heavily looking out for it. Our temperatures, again, are a little bit too high, and would be great if you had some ideas. But let me show you just some pictures. This is the spin balance picture. And now as we imbalance, well, we get way more blues than reds. It shows the color code depending on the state that I'm giving the talk in. Sorry. Okay. Maybe not a good time to make political jokes. Okay, great. So that was one of the joke. Okay.
Almost like this is the last time.
Oh yeah, this was the last time we made the joke. Okay, great. Okay. So what can we get from these data? I will not show you all the G2 functions, whatever. We see that we get basically a Fermi sea of excess fermions coexisting with the Bose gas, but that Bose gas is already strongly repulsive because these bosons don't want to be near each other because they consist of fermions that like to spread their wings. And that's what gives them a repulsive interaction, non-local repulsive interaction. So it's a cool situation.
So that repulsive interaction it's like a second order fluctuation.
It's a second order fluctuation. So this boson has two fermions in it. This boson has two fermions. So this boson wants to sometimes spread its wings, have a spin up, fluctuate this way, but then this guy cannot fluctuate its spin up on the same
It's
side.
strong enough to see.
So yes, and that is absolutely seen. Actually, since you ask, I can show the G2. But yes, so it's they bosons So we find that bosons repel. Man, since you asked, he asked, this is question. Where do we go? So bosons repel. Bosons repel. This is the G2 function for the bosons, one distance apart. You know, that's of course the first strongest signal. It's all negative, so they all don't like to be near each other. Even one-sided wave, they don't like to be near each other, right? That's cool. And then the singlons, the excess fermions, normally usually also don't like to be near the bosons because of the same idea. But there is a certain magnetization at which it becomes favorable for them to sit next to the bosons. And do I have the plot? Yes, even better to sit at 1,1. So that's the diagonal corner. And I think, I mean, the data is messy in error bars, but it clearly crosses 0. And that means if you think of a happy charge density wave of these bosons, the excess fermions like to be right in the middle at the diagonal point. So this, of course, here just the hot fluctuation, but like at low temperatures, it might foreshadow an interesting state where you have a spin and charge density wave. Cool, but I'm done. You survived until the end. You see what we're after. We have all these interesting quantum many-body systems. I didn't talk about the rotating gases, which show weird hydrodynamic instabilities. But these days, it's fascinating to try to do this with single atom resolution imaging. And here are some first glimpses of these rotating gas experiments with single atom resolution imaging. The hope is to extend these single atom studies to also quantum Hall physics. That's a big mouthful, but that's an exciting prospect. So with that, I would like to thank my group and you for your attention.
Hey, thank you for this exciting talk. We have time for a couple of questions, and we start with questions from students who made that rule. Is there a question from a student?
Let's make it awkward. It's good.
Yeah.
If you go back to the symbols, so I say during where the correlation length sort of increases and then decreases between the interaction strength.
Yeah, maybe this one.
Yeah, but I think about this, so here you're plotting like moment position fluctuations, but if I just look at like correlation, but I think about this as being like a probe for sort of moving through the dome of that superfluid, like sort of extended phase that you're moving through on the slide earlier.
Yeah, so
I'm just trying to understand, yes,
Yeah.
you have this like dome of like superfluid plus like dark and superfluid.
right.
But I think you're like actually scanning across that, and the length of these correlations is like some intensity of how you're in this like extended phase, or how do I think about correlation?
Yeah, so already for maybe first to see is that already without any interaction, you already get a correlation. Like that's just the Pauli Fermi holes, one interparticle spacing. If you look at the up-down correlation function, which we also have in the paper, that would be 0 at 0 interaction strength. But from then on, it starts growing because now the ups and the downs are becoming correlated, and that correlation length becomes quite large at 6. Why? Because that's the strongest interactions. When the interactions are on the order of the bandwidth, that is actually where fluctuations are good, and that's where the TC is largest. If you ever make it there, we're at like 0.3, TC is probably 0.2. That makes sense. The largest fluctuating pairs, tunneling is still strong compared to you, so they can spread their wings. So that's why it's a large correlation. But as you now crank up you further and further and further, now you make these pairs very localized again. They don't like to spread their wings anymore that much. And by the way, TC also goes down because these pairs become very sluggish. So the effective mass becomes very large, and so TC goes down.
And so should I think that now if you did have like tunability over your temperature and you now fix it some UT into down in temperature, that your correlation then would just increase?
I don't think it will increase for this one. The pairs we actually saw, you can actually compare the pairs that we see with pairs that you would get from BCS theory. So you could call BCS theory, but like BCS theory, And actually, the pairs look very much already like the zero temperature entities.
But so does that mean that there's like some, like, even as I tune down the temperature, there's some like asymptotic limit of my correlation?
Yes, so the pairs are already at our temperatures pretty well formed as the final pairs that they would look like almost, not
Yeah.
perfectly, almost at zero temperature. But what happens then at TC is that these pairs start to become coherent and they start to actually have the very same wave function and do a Bose-Einstein condensation basically, right? So that's what TC is. Whereas the pair formation happens earlier,
Yeah.
and we see apparently the pairs are already well formed and have already pretty similar character to the zero temperature expectation.
Okay.
I guess I'm curious, how do you prepare the thermal gradient in your Foxtrot?
Yeah, so this was actually a snapshot of a second sound movie. So this gradient, and we have various ways to do this. So this was actually already a snapshot of after having created the second sound wave. Now we have various ways to do this. You can drive the walls, you can shake the walls at the frequency of the second sound. Since it's a resonant drive, you will excite mostly second sound and not first sound. So even though you use a density probe, the potential acts on the total density, thanks to the coupling between density and temperature, that actually drives a heat wave. That's one way. We also have this flamethrower thing, where we actually literally have a laser beam that it writes a grating on one half of the box. So and we just modulate the intensity of that guy wildly, creating all kinds of sound waves at high frequencies, 2 kilohertz or so, which are heavily damped as you saw before. So that produces lots of local heat, and then we stop, and then we watch it go. So that's another way to do it. And do we have another way? Oh yeah, okay. So that was. We have a gradient that we can move up and down and shake the gas. Just similar idea. Yeah. So all kinds of different ways, which gave rise to these different data points. You saw these colorful points. We had various ways to do it, and we wanted to be super sure that we always measure the same thing. So we could oscillate the frequency. We could do a free evolution of the system after having resonantly shaken it, or use the local flamethrower / heater, and we always measure the same thing. We're just trying to do a good job. So yes.
So I know this is not the direction that you've been thinking about this, but seeing the overtone in the spectrum made me wonder, how high could you push up the phononic nonlinearity? Could you increase the Q by going to like a 1D system? And like, could you see single phonon nonlinearities?
Yeah. So we are, of course, super far away from the single phonon thing, but 1D would help. I don't know what then breaks down in terms of, the many-body physics completely changing into some weird tongues. I don't know, gas, right? Definitely super interesting. But we are so far from single phonon that it does blow my mind to think about single phonon. Yeah. No, but it's good to think about it. But
You wouldn't have long range.
I'm too far away from it to now have anything intelligent to say about it. I think that that is very cool though. But we are live. It's not.
Yeah, I mean, I guess my question is, does it end up coming down to like, at the end of the day, the relationship that we would see or something, the lifetime that sets it, or are we ending up in like a 1B thing where I'm talking about exciting one of 2 atoms or something dumb like that?
Yeah.
Actually,
Complicated question.
on the fractional quantum Hall side, what's your thought for how you compare the like a couple of the order state?
Right. So the best. So I think the best substance to do this with is again lithium-6, so strong interactions. And if you want to do it with bosons, well, do it with molecules. And the molecules near Feshbach resonance, they interact super strongly. So working with sodium is probably not the greatest idea, even though we'll probably start fun because the interactions are super weak. But for the fermion pairs, I get super strong interactions that should govern the scene. Now, whether we can cool into a low temperature phase of the soup, or whether we first see again some hot soup, I don't know. The way we do it so far is of several ways, but one new way to get into interesting things is we spin up our gas in this harmonic trap. We rotate an anisotropic saddle potential, and then you get this very elongated soup here. This very elongated thing. That's actually already Landau gauge wave function. So it's many bosons, maybe 100,000 or so in one Landau gauge wave function, which then breaks up into these puddles. That's all mean field physics, of course, still, but it actually gets us automatically into strongly interacting regimes as we go more and more dilute, first of all. If you just squeeze longer, at some point we get to the regime where we have one particle per flux quantum, and interesting things are supposed to happen then. So these images down here were done in the regime of having 10 particles roughly per LB squared. And yes, I mean, still overall looks like mean field physics is happening, but now we can actually see what the individual atoms are doing. And the very first thing I want to see is whether the G2 function is starting to develop an interesting sort of hole, because the guys don't want to be near each other, as you would also expect for the Laughlin wave function.
But your claim is that just by getting closer and closer to that instability, you're adiabatically approaching a Laughlin state. Like, are you going? I'm just wondering, is this a low entropy state that you're making?
No, I don't think. I don't
low
think.
entropy. Is there even a suppression?
So microscopically between the two guys, I'm pretty sure they will not like to be near each other. In fact, they will actually rotate about each other. So I'm sure that physics, that local physics, we will see even if you are not at the ground state. But so this is clearly not the ground state, because the ground state would be all these atoms being infinitely far away from each other. So what we have to have is what we have here, a box that confines them so that they cannot go anywhere. And we have to have some sort of way to actually remove entropy again after we have filled it. We can do this, let them fill it in, but that will create a hot soup, relatively speaking, and we have to have some way to actually remove.
Oh, I see. So you're not talking about making low entropy droplets in this thing. You want the whole thing to be
eventually. Eventually. I mean, the droplets are also cool to think about. It is already interesting dynamics in the. So, for example, this you would mimic as like you start with everyone in one Landau gauge state, k equals 0, and then coherently through interactions they form k and minus k pairs, which is causing this instability, which is kind of cute. And that's already dynamics in the lowest number level. It's interesting to study that and look at the G2 function, how it evolves. But this is not getting into the absolute ground state, because the energy, if you just conserve energy, is not the ground state, right? So we need to be creative and find ways to remove entropy. And we do want to have the box so that we actually fill the whole scene with rotating fermions.
Are you going to try to use some evaporation or something?
Yeah, it's a little delicate because I don't know how we get them out. Maybe maybe we have to suck them out through the bottom, right? I don't know. Yeah.
Can I ask one last question on that topic? So you asked us for ideas for everybody. Get older, but probably you have some creative ideas of your own.
Yeah, so we're actually working on one thing that's I find super exciting. So we have this bilayer that so far we have used for imaging, but you could also make a super nice band insulator in one layer, and then coherently let the atoms explore the second layer. So that should give you n=1 mod insulator in both in the bilayer system. And if you want, after that, you could even split the two layers, make them decouple them again, and then you should have two very cool copies where hopefully the entropy is in the the mutual entropy between those two layers that you don't care about. That's one hope that this bilayer helps us. We also think so that would be great. The other thing is you try to create as best as you can some spin mixture down here in the lower layer. And so far we always see that there's few excess fermions that we're not supposed to have thermodynamically speaking. And those might be actually the ones that don't allow us to go to lower temperatures. And we hope we can suck those away by driving them up into the second layer. So I don't know. Well,
Can you use your spectroscopic techniques again? Like, is there enough binding between the Laughlin pairs? Spectroscopically shift some RF?
That would be amazing. I would hope.
Throw any ones that are not shifted.
I think it's not crazy to think about that, because the interactions are really strong. We can make them ridiculous, right?
Just do your own technique.
So maybe we can do some RF evaporation technique, where you drive them into some other thing and then have a creative way to suck them out. I don't know, but this is going to be fun to play.
Okay, I think in the interest of time, we should wrap up and thank Martin one more time.